Greetings everyone, back on the messy bench is the JAT801 Amplifier project. The last video I made on this thing, I was complaining that I didn't think it was stable. Well, I was just being too hard on it or too dumb, when in actuality it is just fine, and that's what I'm going to demonstrate in this video. But to get to that point, I'm going to talk about the amplifier's compensation. I'll give you a 10-cent tour of compensation, what it's all about. So it's not going to be any charts or graphs or things like that. Just kind of a basic overview. Well, you'll hear it often called negative feedback compensation, sometimes frequency or phase compensation even. Take a drink every time I say compensation, and you'll probably be pretty woozy by the end of the video. What compensation is essentially a low-pass filter within the closed loop of the amplifier. And I mention that because the input and output filters are outside the closed loop, so they are not part of the compensation, though they do help in some ways with the amplifier's compensation, and we'll see that later. Let's say we did not compensate this amplifier. Well, we would find that its frequency response would extend up into the megahertz region. The trouble is, as the signal travels through the amplifier circuitry, there are some accumulated delays. In other words, the phase of the output is not in phase with the input. And at a very high frequency, that could invert the phase at the output. So this is where I have to talk about negative feedback. So what we do is take some of the output signal and feed it back to the input of the amplifier. This amplifier uses a differential pair, and we feed it back to what's known as the inverting side of the differential pair. What that does is make the signal 180 degrees out of phase from the input. And that signal is used to allow us to set the gain of the amplifier. It's also used to correct nonlinearities and noise in the amplifier, makes the damping factor extremely high. So it's essentially a control signal for the amplifier circuit. Well, without compensation, at a real high frequency, that signal going back to the inverting pin has had so much phase shift, it is no longer an inverted signal. It's no longer 180 degrees out of phase. It could accumulate enough phase shift in that it's now in phase, in other words, positive feedback. And in the case of the amplifier, it'll make it oscillate, and that's something, of course, we don't want it to do. So what compensation does is to roll off the frequency response of the amplifier so that the accumulated delays do not make the signal all the way 180 degrees out of phase. There is still going to be some phase delay, but it's not going to be enough to make the amplifier oscillate if it's designed properly. To put it another way, the gain of the amplifier at which the frequency would make it unstable would be so low that there's just not enough signal there to make it oscillate. However, we just don't set it up to be good enough. We want to have safety margins, because depending on the different loads, the effects of components, the capacitance and transistor junctions can be different at different voltage levels. If we put capacitive loads on the output, that can cause additional delays in the circuit, which could make it oscillate. So, like I say, we want a safety margin, and that's where you hear the terms gain and phase margin. And for example, for phase margin, something like 45, 50 degrees. One time I went to see the Grand Canyon. We went on this Indian reservation, and we went to the edge, literally went to the edge of the canyon. There's no safety fence or anything. Well, I could have walked right up to the edge of the canyon and looked down. But I stood back. I gave myself a little safety margin. For if there was a breeze or I stumbled or something, there would be no John Audio Tech videos. You'd be watching Bob's or Joe's Audio Tech channel. You wouldn't have cared because you wouldn't even known of John Audio Tech, but so yeah, we want to have some safety margins. So compensation ends up being sort of a compromise. We still want the amplifier to be fast enough that the slew rates are pretty high. It gives negative feedback the headroom to keep distortion and noise low and damping factor high at higher frequencies. However, in doing so, we're not giving ourselves a lot of safety margin. However, if we use too much compensation and make the frequency response really low, we slow the amplifier down too much. We don't give negative feedback the working headroom that it needs. Well, sure, the amplifier can be more stable, but it may not give us the performance we want. The type of compensation I use in my amplifier designs is called Miller compensation, and I don't want to get into a drawn-out discussion on that, but there's more advanced types of compensation. There's what's known as lag compensation, which is really inferior to Miller compensation. Miller is just, in its simplest form, it's just one capacitor, but it has so many benefits over lag type compensation. Now, one thing I want to say before I move ahead here is just because you design the amplifier and you look at the Bode plots and all that stuff and find that the amplifier looks stable, doesn't mean it can oscillate. The amplifier can oscillate due to poor layout. If your supplies aren't bypassed very well, your ground scheme is not done very well. The amplifier could oscillate around local loops. If you remember the JAT801 prototype here, the amplifier was oscillating around its output stage. Usually a local loop oscillation is a high frequency, and in that case it was around 40 megahertz if I remember correctly. Even though the compensation used for the global loop of that amplifier made it stable, well, it was still oscillating due to the output stage, so I had to correct that. Now, I like to attempt to stimulate my amplifier projects into oscillation by doing a few tests. I'll lower the value of the Miller compensation capacitor to reduce the safety margins. I also load the output with pure capacitance, and in doing so, that adds an additional phase lag to the circuit. They call it adding excess phase. And then I'll stimulate it with square waves. A 10 kilohertz square wave with fast rising and falling edges and sharp corners is plenty to attempt to stimulate the amplifier to oscillate. So how fast a square wave do you actually need? Just look at your oscilloscope. If it looks good on the scope, it's good enough to test with the amplifier. Okay, so here's my setup. So I have the amplifier, connected it to my load here. I made some short leads. I don't have the output coil in. The output coil is used to help isolate the amplifier from pure capacitive loads because, like I say, these amplifiers do not like to drive those loads because of the excess phase it would add to the circuit. But it is being kind of hard on the amplifier in doing so. It can make it oscillate. And one reason I talked about compensation is, in the last video I mentioned that the 501 didn't oscillate. Well, it turns out I'm actually using more than enough compensation in that amplifier, and it makes it stable. When I talk about hot rodding the 501, I'm going to talk about reducing that Miller compensation capacitance so the amplifier can run faster and get better performance. Although I thought it had excellent performance at high frequencies when I did the intermodulation tests. And I kind of question, with normal music, there's not a lot of energy up there. And if there's not a lot of energy at high frequencies, in other words, small signals, it's not going to produce really anything from intermodulation effects back into the more audible spectrum. So yeah, I question that. It's just a spec sheet thing. It makes the amp look nicer on the spec sheet. If it's really audible in real use, I doubt it. But, we'll go through the motions here. Well, we had our first lockup here. This menu moved over here and it doesn't do anything. We'll just turn it off, turn it back on. Okay, we got it going here. There's a lot of glare. I'm going to have to shoot with my light turned off probably. And this is a fast enough square wave. There is an overshoot here, but yeah, we're looking at the output. The reason for that overshoot is I have seriously lowered the Miller capacitance value of the compensation cap. I started out with 100 in the last video, and now it's at 22, very low. If I calculated properly, it should be around, it should be stable down to at least 50 or so. So let me adjust this. It doesn't oscillate though. There's that overshoot, as I said. So let me load the output with the capacitance and see how it behaves. Okay, so I added a 103, which is a 10 nanofarad. Usually I start to see instability start around 100 nanofarads or so. Again, I'm not using an output coil. And look at this. Now, this is where these oscilloscopes, these cheap oscilloscopes, can lead you astray. It looks like there's instability upon instability because the oscillation's got its own wigulation. That is just the aliasing artifacts of these oscilloscopes. So if you zoom in, you see it's just a steady oscillation. So yeah, 22 microfarads of Miller compensation is not getting it done. And I like to sweep the amplitude of the square wave because, see, around clipping it looks fine, but yeah, it oscillates. Matter of fact, and that's another thing with these cheap scopes. It seems like it's not oscillating now, but let me turn up the amplitude here and turn the signal all the way down. And let's turn it up more. Maybe it isn't oscillating. Well, I turned it up. No, it doesn't continue to oscillate. It just requires that square wave stimulus to make it oscillate, so it's marginally stable, I guess you could say. Okay, same setup with the 10 nanofarad, but this time I added the output coil with its parallel resistance. This is what it looks like on the schematic. So this output coil will kind of isolate the amplifier's output from the pure capacitance load. That's the whole idea, since these feedback amps don't like to drive pure capacitive loads. And you can see, well, it made a heck of a difference. It doesn't oscillate no matter where I set it, even with 22 picofarads of Miller capacitance compensation. And it looks like it's jiggling around. Again, that's an artifact. You just have to zoom in and you see it's a steady ring there. But would I consider this stable enough? It would make for a nice fast amplifier, but I still want it to be stable with more capacitance. I want it to be stable up to 1 microfarad, and no amp should be driving anywhere near that normal use, but it's just a stability test. It must pass. Okay, so I went up to a capacitor marked 104, which is a 100 nano or 0.1 microfarad. And it's got a pretty healthy ring there, but as I sweep the signal, I don't see any breakout and oscillation. I probably should turn that down a bit. You have to look at the signal all the way to clipping, and it's all the way to clipping. I'm actually surprised that it's not oscillating even at 22 nanofarad Miller compensation. So I can change the value of the compensation cap. I took out the original one and put these sockets in so I can switch cap values around easily. So I'll leave it out and turn the amp on. Now I lowered the current from the supply because stuff will get hot, burn up. Even with no signal, it's an oscillator. See that? And when I was playing around earlier, something was starting to smell over here. I think maybe this resistor was getting hot. So I'll turn that thing off. Yeah, gotta abuse it a little bit, right? Okay, so now I plugged in a 68 picofarad. That's the value I recommend using this amp at. And we still have the 104 in there. And stability. Oh, I gotta turn the light back off again. Apologies. You can sweep that from clipping to no signal. And that's what you should see with a capacitive load. You'll just see a ring, provided you're using fast enough sine wave. Okay, worst case scenario, I have a 1 microfarad cap across the output. And I should mention, this is very hard on the amp. If you just start doing these tests on an amp, you can draw the magic smoke. So do at your own risk. So as you increase the capacitance, the ring becomes a lower frequency, and it looks like it's extending across the whole waveform. But if you lower the square wave response, you see it's just a ring. It's not an oscillation. See, if you increase it, it looks like it's unstable, but no, it's fine. You should absolutely never see that type of capacitance loading across the amp. And things are getting hot here, so I'm going to shut the power off. Okay, so I swept the level. I did capacitive loads unloaded at 4 and 8 ohms, and nothing I could do would make this oscillate. So I consider this amp to be perfectly stable. I do have to retest when I get the paralleled output stage operational. I just don't have the room with these big transistors on this board. And I got this thing nice and toasty. Gonna let it cool down here. Well, before I close this video out, I'm curious of how the TDA 2050, which is one of my favorite chip amps along with the LM1875, just want to see how its stability is with capacitive loads compared to this one. Well, you can't really adjust its Miller compensation. It's baked in internally with the IC. I mean, you can use caps in the negative feedback loop, but the data sheet doesn't call for that, nor does it call for a coil on the output. And I've used these amps just fine without problems in a lot of amplifier circuits, so yeah, let's hook it up and see how it performs. Okay, I have no capacitor now. This is its square wave response. I have a weird glitch on the negative side. There's clipping. It goes away at lower levels. There's a weird little ring. There's almost a little oscillation there, isn't there? See that? On the bottom? It's almost unstable right around clipping. Okay, now I have the 0.1. There is no coil in the circuit yet. Ooh, I don't like that. It oscillates. It clears up with no signal. You know, a very unstable amp would just continue to oscillate, but yeah, I'm going to add the coil in and see how it behaves. Okay, now with the coil on the output, it's the same one I used on the 801. Same 0.1 microfarad cap. So it's a little worse on the negative side. Go towards clipping. Oh, look at that. There's still instability. And usually that's where you find instabilities, often just before clipping. Not always, but I've seen where you sweep it and it just goes unstable at a certain voltage level, so that's why you sweep it. Right there. Even with that coil, it is still unstable. So what this needs is probably a larger value cable. This is around 1 microhenry. Well, again, this is a strenuous test that is tough to pass with flying colors. And yeah, even with the coil, this amp still oscillated. And this amp is just fine. There's nothing to worry about. But again, I've used this amp with no problems, though I still recommend using these chip amps with the coil on the output. The LM1875 is a little more stable without a coil, that I found out, but still it's good to use a coil on its output. And it's not a big deal to add one, I think. But yeah, I'll stop it here. The video's going on long enough. I got a couple other issues I need to figure out with this circuit, and hopefully we can get somewhere. But yeah, I got a couple more videos. Was hoping this would take 2 or 3 videos, this project, but no. Run into the problems, and it's going to take more. But I'll stop here. Thanks for watching, and we'll catch you on the next one.